Let's take a look at number 77 here. So really the crux of chapter 11 is all about this, this diagram that I've drawn on the board probably a countless amount of times by now. So chapter 11 is all about different conversions and using the mole ratio in particular to go from one part of an equation to another. But really the most common conversions you're going to make involve going from grams of one substance, we'll call this substance A, back and forth between grams of that substance and moles of that substance, from moles of one substance to moles of another substance, we can call that substance B, and then from moles of substance B to grams of substance B. Whenever you go back and forth between grams and moles of any substance, you use molar mass. Whenever you go back and forth between moles of one substance and moles of another substance, you use the mole ratio. So really the mole ratio is the key new concept that's introduced in chapter 11. The important thing to remember is that there's no direct way to go from grams of one substance to grams of another substance. Where problems get a little bit more complicated is when we add steps to the beginning of this little diagram here. So if we have to do some other step to get to grams of substance A. And trying to find the limiting reactant is one way that these problems can become more complicated. Limiting reaction type problem, your first step is determine the limiting reactant. And once you get the limiting reactant, you can use that as your substance A. So you can go from grams of your limiting reactant to moles of it, then from moles of limiting reactant to moles of your product, and then from moles of your product back to grams of your product. Number 77 is one such problem. So in this case, you're given molar amounts of both of your reactants. And one giveaway as to whether or not something's going to be a limiting reactant problem is if you're given amounts of both reactants. So in this case, you are. You need to figure out, first of all, what your limiting reactant is, and then use your limiting reactant to figure out the moles of iron hydroxide produced in this reaction. So you're told you start off with 8.0 moles of this NiO hydroxide substance and 5 moles of iron. You can determine what your limiting reactant is by comparing what you have. So again, this is what you have, you were given that in the problem, to the mole ratio from your balanced equation. So in this case, we're starting with 8 moles of this NiOOH and 5 moles of iron. So you can figure out the ratio of iron to NiOOH by dividing your amount of NiOOH by your amount of iron. Right, we could also think of it as we can start off with 5 moles of iron to 8 moles, 8 moles of NiOOH. In order to serve as a standard of comparison, I usually like to have my ratios so that they have 1 of whatever substance is on the left side. All right, you can get 1 by dividing both of these numbers by 5. All right, this is basically what we did in that fraction to the left here. So if we divide both numbers by 5, we'll have something like this: 1 mole of iron to 1.6 moles of NiOOH. You can compare the ratio of what you have to the ratio given by your balanced equation, and you get the numbers from the balanced equation from the coefficients in front of iron and NiOOH. So the balanced equation says that each mole of iron will react with 2 moles of NiOOH. What you have is you have 1.6 moles of NiOOH per 1 mole of iron. This indicates that you don't have enough of this NiOOH because that number is less than what is called for in your balanced equation. So that is your limiting reactant. If for some reason this number, so the second number, was greater than the 2 moles, then that reactant would be in excess. It's called in excess, and your other one would be limiting. But in this case, 1.6 less than 2, so NiOOH is limiting. That's our first step out of the way. Once we figure out which of our reactants is limiting, we can use the number of moles of that reactant and the mole ratio to get our moles of our product. So now it becomes one of the problems we've done earlier in the chapter. We identified our limiting reactant. We used the mole ratio to cancel out our moles of our limiting reactant and get our moles of our product. So the final answer to this problem is 4 moles of iron hydroxide. In problem number 80, you're asked to identify the limiting and excess reactants given the gram amounts of both of your reactants. In this case, you're not given an equation, or at least you're not given a balanced equation. What you're told is that the reaction of chlorine gas with solid phosphorus, which is P4, produces solid phosphorus pentachloride. So the first step you got to do here is write a balanced equation. One thing you need to remember is that chlorine gas is diatomic. So you got to make sure it's Cl2. From there, you use your naming rules. Right? Phosphorus pentachloride is a molecular compound. So when you see penta, you know it means 5. So the formula for phosphorus pentachloride is PCl5. We use the mole ratio to determine what our limiting reactant is. So you don't use the ratio of masses, you use the ratio of moles. And again, what you want to do is you want to compare the mole ratio you have to the mole ratio indicated in your balanced equation. So we're looking at phosphorus, P4, and chlorine, Cl2. First thing you got to do is you got to convert your masses to moles. You do this using molar mass. Divide each of your gram amounts by the molar mass of whatever compound that is. In this case, Cl2 has a molar mass of 70.9 grams, and P4 has a molar mass of 123.9 grams. That'll give you 0.226 moles of chlorine and 0.186 moles of phosphorus. We can get our ratio of chlorine to phosphorus by dividing the amount of chlorine by the amount of phosphorus. That gives us 1.22. What this means, right, is that we have 1.22 chlorine for every 1 phosphorus. According to our balanced equation, each P4 will react with 10 Cl2s. So if we compare what we have to the balanced equation, our second number is smaller than the number called for in the balanced equation. That means we don't have enough Cl2. So our chlorine, therefore, is limiting, and the reactant that's not limiting is in excess. P4 is in excess. So that is number 80. Limiting reactant problems add steps on to the beginning of that diagram I drew earlier. Problems involving percent yield add steps on to the end of it. So what percent yield is it's basically how efficient your process is. And you can determine the percent yield by comparing your actual yield, so the amount of a substance you actually get, the grams of your product that are actually determined, and you're told that number, right? So you're given the number of, or the grams of your actual yield. You want to compare that to the theoretical yield, which would be the grams of your product you're supposed to get. And you determine that using your balanced chemical equation. So the key to all these percent yield problems is determining that theoretical yield. So in number 94, you're given a balanced chemical equation. You're given the amount of one of your reactants, and you're asked to calculate the percent yield of a reaction if 5 grams of one of your products is obtained. In that case, the product is zirconium. So your first step is you want to calculate your theoretical yield here, the amount of zirconium you're supposed to get. And you do that by going from grams of zirconium to moles of zirconium, from moles of zirconium to moles of zirconium iodide, and from moles of zirconium iodide to grams of zirconium iodide. Okay, so what we're going to do here, we're starting with ZrI4, so kind of the opposite of what I just said there. So instead, we're going to go from grams of zirconium iodide to moles of zirconium iodide, moles of zirconium iodide to moles of zirconium, and then moles of zirconium to grams of zirconium. All right, so we can go from moles of ZrI4 to grams, or grams of ZrI4 to moles of ZrI4 using molar mass. Step 1, done. Our grams of ZrI4 cancel out. Now we have moles of ZrI4. We can go from moles of our reactant to moles of our product using the mole ratio from our balanced equation. Coefficients tell us that this mole ratio is 1 to 1. Final step, we can go from moles to grams using the molar mass. Right, we make sure grams are in the numerator because we want those. We want to cancel out moles, so moles in the denominator. So the theoretical yield for this is 6.85 grams. That's the amount of zirconium we're supposed to get. You're told in the problem that your actual yield is 5 grams. Formula for percent yield is over here under this nifty now double arrow. Okay? From here it's just a matter of plugging in your actual and theoretical yield. In this case, you end up with 73% for your yield.